Let's do the equilibrium questions. Nitrogen dioxide is brown, so this is brown, and is a colorless. Right. Before we start, let's revise this. That tells you the reaction. Right, we're going through this slowly. Reaction is reversible. You should know this by now. Now, what does this delta H tells you? The delta and then the H is change in enthalpy. Enthalpy is change in heat or change in energy or heat energy. This here is delta. It's capital D in the Greek language. Right, one more thing for now. This minus, this negative change in enthalpy tells you it's an exothermic reaction. So what I'm going to write down is the forward reaction is exothermic. The forward reaction is exothermic. Okay, done. Right, there you go. Let's rub these out. Do we need to rub these out? No, we don't. Let's rub these out. Right, okay, let's start again. Right, so that's that bit done. What we're going to do is we're going to split this as usual. We look on the left hand side, we see so it's exothermic, so this side is hot and this side is cold or cool, right? We've also got the fact that you've got 2 moles here, or molecules or particles, and 1 here. I'm not talking about atoms, remember, we're not talking about atoms, we're talking about the number that's here in front. And because there's nothing there, there's a 1 there and there's a 2 here. So now straight away we can say this is the high pressure. Run out of room. Pressure is high. So this will be low pressure. Okay, that's that done. Right, so now we're going to look at 20 degrees C. Go up. Yes, okay, it's 20 degrees C, and now it's gone to 60 degrees C. So we've increased the temperature. Let me get this. So we've increased the temperature. The system wants to cool down. It wants to go to the cold side. So it'll come to this side. So the equilibrium, so we can say the equilibrium. That means this reaction is going to go left. It'll be more going in that direction. The equilibrium shifts to the left. Now what? Alright, what else is there? Temperature and position of the equilibrium. Right, okay, it just shifts to the left. That's it. It's not 2 markers. They're not asking so why. Predict the effect of the increase in pressure. So here we go again. So we're going to increase the pressure, and then the system wants to go to the low pressure side. So the equilibrium will shift to the low pressure side, which is this side. So we can write the equilibrium shifts to right. The equilibrium shifts to the right. That's it, one marker. Suggest why it's difficult to predict why the which way the equilibrium will shift right, because look, the temperature, let's write it here. Okay, don't know what to write it now. Right, because the temperature shifts it to the left, the temperature shifts it that way, and the pressure shifts it to the right that way. We don't know which out of these two is bigger, so it is difficult to know, to predict which change has a bigger effect or greater effect. Okay, again, I won't worry about this. Just keep practicing these and eventually it'll sink in and it'll go in. Suggest why the equilibrium mixture is darker at 60 than 20. So, right, so remember we said it's an exothermic. So at 60 you're gonna get, let me get this right, it's darker shade of brown at 60. Okay, if it's right, so what we can say, I'm going to write it right up here. It really, we expect it to shift with temperature. Let me get rid of that, because this is the cold side. At 60 degrees we expect it to shift in that direction to the cold side, because we've increased the temperatures higher. But what happens is the effect of pressure pushes it that way, so the effect of pressure is greater. Again, don't worry about this. Look, we're just linking this to what actually happens, right? So we can say the proportion, or proportion is a better word. Proportion of nitrogen dioxide is greater, so that's why it's darker. Why? Because an increase in temperature is greater than let me just get rid of that. Temperature, go back, has a greater effect than increase in pressure. And we found that out because it's darker. Initially we didn't know here. You see that here? We did not know which way it would go. They've given us a scenario and we've said, right, okay, that's the reason. Right, let's carry on. Right, so we're looking at these three reactions, 1, 2, 3. What do we notice straight away? That's positive, so it's gained energy, so it's endothermic. This is negative, so it's going to be what? Exothermic. This is going to be endothermic. Again, endothermic means it's going to gain energy. Let's run through these quickly. Right? You've got 1, 2, 3 moles here, or molecules. 1, 2, 3, 4, 5. Remember there's a invisible one there, so we've got 5 molecules here. I know straight away this is going to be the high pressure side, so that will be low pressure. Now one other thing, because it's endothermic, this is going to be the low. Let's try another color. Oh, try another color. This is going to be low. Oh, come on. Hello. Nope, it's playing up. I don't like it when it does that. Playing up. Let's play it up. Let's try it again. Right, that is going to be. Let's try that. Let's try that. No, it doesn't like it. Just bear with me 1 second, please. Okay, we're back. Yep, it's working. Right, so this is going to be low temp. This is going to be then the high temp. It's going to be the opposite. And if you do the same thing with these, then it'll give you an idea. For reaction 1, predict whether pressure should be low or high to give the greatest yield. Remember we said yield is how much product or percentage of product. So it's like saying, look, if I had 1, 2, 3, 4, 5, if I had 5 seeds and 1, 2, 3 grew, 3 out of 5 have grown. So as a percentage, that would be 60%. Yeah, so now if I had 1, 2, 3, 4, 5 and 1, 2, 3, 4 grew, it would be 4 out of 5 times 100, which would give 80%. So this bottom thing here has got a higher yield. It's got more products. Okay. Right, okay. So you've got, if we're looking for reaction 1, pressure, high or low. So look, if you increase the pressure, the system will go backwards. We don't want it to go backwards. We want it to go to the product side. So we want low pressure. Why? Because the forward reaction, all right, okay. It's probably easier wording it this way. Let's word it this way. Let's not word it. Oh, let's not word it that way. Just to keep it simple, right? Okay, right. The number of molecules or moles on the right hand side is less. Right, okay. Okay. Temperature, yield. Right, temperature and yield. 1 second. So for reaction 1, we want to work out whether temperature should be low to give the greatest yield. So it's endothermic. So we need to increase the temperature. So if we increase the temperature, the system will go down to the low temperature side, which is where we want it on the right hand side. So what we do is we use increased temperature or use a high temperature And the reason is because the we can say the forward reaction is endothermic. Forward reaction is endothermic. There you go. That's more than enough. That. For reaction 2, suggesting why changing the temperature will have less effect on yield of products. For reaction 2, right? Okay. It's because it's, if you look here, forget everything else, but just look at the numbers here, right? That's 165,206. They're bigger, much bigger than 41. Yeah. So that's the reason. So it's right. We've got it there. So we can say the change in enthalpy is small, so has less of an effect. So temperature has less of an effect. For reaction 3, predict the effect of the rate of forward reaction by increasing pressure. Right. So reaction 3. Right. Okay. Let's focus on reaction 3. So we draw a line down here. We count up the number of molecules or moles. 1, 2. So we've got 2 here. We've got 1 plus 3 is 4. So this is the high pressure side, and this is the low pressure side. Forward reaction increasing the pressure, right? Okay. If you increase the pressure, the system, remember the system wants to go back to its normal. So if you increase the pressure, the system goes to the low pressure side. It goes to the opposite way. So it's going to go to the left hand side. That will decrease the yield. The yield will decrease. Right. Effect the rate. I'm answering another question. Oh my goodness me. I always do this. So we're looking for the rate. Right. What we can do is, this is what they're trying to say. I've got a box here. I've got the same box here. I've got 4 in there, but I want to increase the pressure, so I add a few more. Now this has got high pressure because these particles are hitting the wall more frequently, right? And pressure is force acting on an area, right? So this will be low pressure. So if you increase the pressure, the rate of reaction will increase. Right? Why would that be? Because you have, we can say, can you see the particles? There's more particles, so the particles are closer together. Right? So you have, so particles will collide more often, collide more often with energy greater or equal to the activation energy. Activation energy. More often, right? So look, we've got the keywords in, so they're closer together, and the particles will collide more often with the energy greater or equal to the activation energy. or you can write it this way. Look, where do I write it? I'm going to write it here. Look, I'm going to write it here. I'm going to write it in a different language. Yeah. Particles are closer together. Particles are closer together. So have more successful collisions per unit time. Right. Yep. That's more than enough. That. Right. Right. We're not interested in this. In this confusion. Right. This is a toughie. This is a toughie. Whoa. No, we don't want that. We don't want that. We want. Right. Let's try to squeeze this one in. Nitrogen dioxide, we've done something similar to this anyway. Nitrogen dioxide is a okay. Right, we're gonna skip that. We're gonna do if we get a chance, we'll come back to that. Right, iodine reacts with chlorine to form iodine monochloride. Oh, okay. So straightforward. Right, remember we know chlorine and iodine are, what are they? Diatomic molecules. That means they run around in pairs. So we know chlorine, so iodine is a pair plus chlorine, which is a pair, and it gives iodine monochloride. So it gives iodine monochloride. There's one of each. Mono just means one. And if you look, we've got two here, so we stick a big 2 there, and that's balanced it out. Right, we're not worried about that. Right. We're being asked about the features of dynamic equilibrium. This question's come up before. So there was 3 things that we had to learn, didn't we? So they say, right, they've actually given you one. Let me just highlight it here then. That both the forward reaction and the backward reaction occur at the same time. That's one. They've done that. So now we need to write the other ones. So we need to write the rate of forward reaction is equal to the rate of reverse reaction. Right, and this is the key, right? This is where it can go wrong. This next one, the concentration of products and reactants remains constant, not the same, not equal, but constant. There's a subtle difference. So we're saying the rate of forward reaction is equal to the rate of reverse reaction, and we're saying the concentration of products and reactants remains constant. When the equilibrium mixture is heated, it becomes darker. So okay, darker. So when it's heated, it goes that way. So this is an exothermic reaction, because when you heat it, the system wants to go to the cold side. Exothermic, the right hand side is always hot. So the equilibrium, remember that equilibrium, forward half arrow, backward half arrow in the opposite direction, will shift that way because it becomes darker. So it's a 2 marker. We say the equilibrium has shifted. Where is it shifted? Shifted backwards. Shifted backwards. So let's just say shifted left to the reactant side. Yeah. So what does that mean? So an increase, because they're asking you this, is it X or endo? So increase in temperature shifts it to the endothermic side, or you can say so this means that the reverse reaction or the product reactant side is endothermic. Right, okay. There's a lot of this nitrogen oxide, maybe that's it. Okay, again, dynamic equilibrium. Why does this feel so familiar? Right, brown gas, colorless glass, colorless. 2 moles, high pressure. 1 mole, lower pressure. Right, a sample of pure NO2 is placed in a sealed flask at 25 degrees C. The flask is left until a dynamic equilibrium is reached. Now what they've done is they've given you the forward and backward reactions occur at the same time. Now we've got to produce the other two. Right, the rate of forward reaction equals the rate of backward or reverse reaction. Then you've got the concentration of reactants and products remains the same. Oh, remains constant. Let's use the word constant. Don't use the word equal. Let's use the word constant. Let me highlight that. I nearly overlooked that. Right. Where has the equilibrium been reached? We can see there. So when it levels off here, it's about straight. Yeah. So the number of moles is decreasing, and then it stays constant. So that means even though you've got 2 on one side and 1 on the other, so the 2 there and the 1 there, it levels out. So it was getting smaller because these 2 were turning into 1, and eventually it evens out. So draw a curve on the graph to show the number of moles of N2O4. N2O4 is that. So look, when you start, there's no moles, and as time progresses, it levels out and then it stays constant. So as this is, it's going to be less steep than this. So if you drop 2 here, you're going to only pick up 1 there. But as long as it's below and then it levels out, it's alright. Right, that's it. The sealed flask contains equilibrium mixture 50 degrees. The mixture color goes darker. So the darker, so that means it's shifted. That means it's shifted left. Right, so first of all we write the equilibrium has shifted left, which means the backward, because what happened was that was where are we? It was at 25. It was at 25 degrees. You moved it to 50 degrees. So the system's gone to the cooler side and it's gone darker. So it's moved to this side and gone darker. So we know this is an exothermic reaction. Okay, so it's gone back. So it means that the backward reaction, the backward means, okay, the backward reaction is, in this case, endothermic. There you go. Right, we'll call it quits there. We're going to start this again because I think repetition on this will be good. Right.